Smart homes can be installed in a code-compliant manner to improve the health, safety, and welfare benefits of the user, and may even save the user some money. The focus of this 2-hour program will be to introduce smart home components and concerns while later walking through the setup of a low-budget smart home with the focus on energy controls. There's a lot to learn, so let's start out with a safety topic. Here's an example where a hacker infiltrated a home and pretended to be Santa Claus. Google later announced one of their web camera partners had a vulnerability which allowed third-party access to home security cameras. Google's response was to cut off access to cameras until the vulnerability was patched. This is alarming, but on the other hand, many users of cameras would be just as annoyed to learn their camera service was interrupted because someone else's camera was hacked. As much as the public is alarmed about internet security, we are even more enamored with cloud services which invite such insecurities into the home. The smart home designer will always invite the risk of failure into the home despite the advantages of smart home technology. Pushing the limits of the technology too far can be a costly error. Cloud services, which require an internet connection, can provide convenience, stability, and value, but that internet connection will always mean the device services could be lost, disconnected, or hacked. Cloud services provide the best voice commands, for instance, ones that have obvious advantage to health, safety, and welfare. Voice controls such as Amazon Alexa or OK Google offer new ways of accessing home lighting and other devices. Home Assistant, the open source home automation platform we will use later in class, has partnered with a privacy-oriented voice service called Alta, powered by the Stanford voice engine Almond, but its features are still in the early stage of development. For now, for voice commands to be useful, they can be easily connected to Amazon or Google cloud services. Voice commands have immediate use. What if an automation accidentally turns off a light that needs to be turned back on? It almost seems natural in a smart home to yell out to turn on the light, so how does that actually happen? It is possible to set up a secure internet connection to Google or Amazon cloud services directly in order to avoid subscription fees. Home Assistant charges $5 per month as a cloud service fee to connect to Google and Amazon in a secure manner. This is not a programming class, so I suggest paying the fee. However, it can be avoided with enough hacking. If you're like me, you might already own a Google or Amazon voice speaker, such as Alexa, in the house. In any event, I don't plan to implement my own voice control configuration, and I'd like to control all of my smart devices by voice using these speakers that I have. So there's no better excuse to sign up for the Home Assistant free trial of their cloud service and get voice commands going. After accepting the invite email, I'm prompted to enable Home Assistant within Google Assistant. In other words, I need to use the Google Home or the Amazon Alexa app to give it permission to talk to Home Assistant. My Home Assistant devices are then pulled into Google Home. Immediately, I can tell Google Home to turn on or off my dehumidifier smart plug. I can make voice command changes to my thermostat settings. I can ask the status of these devices as well. This is cool because my $65 programmable thermostat was not intended to be voice activated, but because of connecting it to the Home Assistant platform, it now has those features. Because it was an Internet of Things device, code has been written by third parties to connect it to voice services. My home is now voice activated using Google's cloud service. But unless I am an advanced programmer, I will end up paying some form of monthly subscription fee for this convenience, even if it's modest. Facial recognition for building security is much more likely to be a cloud service than run on a local computer. A cloud service doorbell that has facial recognition might be more useful than a non-cloud doorbell that lacks it, unless that non-cloud doorbell is connected to a very powerful computer that runs its own kind of facial recognition software as the cloud service doorbell does on a third-party server. Companies are commercially incentivized to fund and develop cloud services. So cloud services are sometimes cheaper or sometimes more functional than a more secure local. Cloud devices are definitely easier to use than local secure devices. But cloud services also invite security risks, such as the visit from the Christmas Grinch we saw earlier, or simply losing access to these devices during external circumstances like a failure in the internet connection. Building design is changing. I like to think of how smart homes could benefit new construction for cost savings. Could the thermostat be installed directly on the indoor unit, eliminating the wire run through the wall? Temperature sensors from any room could serve as the trigger, so a living room mounted thermostat is no longer necessary. How else might building design change? Might power over Ethernet devices require running Ethernet cable to the window curtains, or replacing AC lighting circuits? Is National Electric Code even ready for smart home devices? Let's start with 21070 lighting outlets required, dwelling units, habitable rooms. At least one switch controlled lighting outlet shall be installed in every habitable room, kitchen, and bathroom. The definition of habitable room is not found in NEC, but rather in International Building Code as a space for living, sleeping, eating, or cooking. Bathrooms, toilets, closets, and hallways are not considered habitable spaces. So while not all rooms in the smart home are code mandated to have light switches, code does require most rooms have at least one light switch, but not multiple light switches. So, code is less clear as to whether or not the wall switch must actually be a manual switch like a traditional light switch, or if it could be a wireless switch. But I think an inspector could put his foot down to demand a hardwired switch. There's also the spouse acceptance factor to consider. It would not be in the best interest of the health, safety, and welfare of the inhabitants to invite negative emotional reactions into the smart home by not providing the users with a manual fallback in the event of a smart home failure. This is interesting because some of the smart home light switches require rewiring the light switch and actually taking it out of the circuit, routing the power circuit through a controller tucked away behind the light switch in the junction box, while rewiring the actual light switch as a low voltage relay rather than a traditional 120 volt traveler switch. A particularly hard inspector might suggest that a relay on the wall is not the same thing as an actual electrical switch on the wall. And also the relays do not work as well as a physical light switch physically redirecting the electricity, as the relays only detect flickering voltage of a low voltage circuit circulating through the light switch, whereas a traditional light switch would actually carry the 120 volt circuit through one of two traveler circuits, switching back and forth between the two switches. It is possible to retrofit two-way or three-way light switches, but it's also more difficult to do so than to retrofit a single light switch. It's much easier to install these controllers when there's only one light to control, not two or three, through separate switches. And I do think it is appropriate to have at least one hardwired light switch on the wall in every room, providing power to at least one hardwired light bulb, so that you don't overkill with smart technology and have, all the lights in your home not work because you wanted to have something weird like battery powered light bulbs and no, hardwired light switches on the wall. So I don't think smart homes are ready to eliminate all the wires from all the walls. In fact, I think for new construction, I'd caution a smart home designer to remember that battery-powered devices, which mount on walls or ceilings rather than doors or windows, will usually have a powered by USB or powered by Ethernet option. In new construction, it's usually a better choice to go with a hardwired power option rather than to rely on batteries so that the device can be used more frequently and no longer require the batteries to function. The batteries could then be useful in power outages as well as to address other power quality issues. Now, power quality issues are particularly close to my heart as I'm a solar installer. So LED lighting is powered by DC current, but AC current is easier to transmit by the utility. So each DC light bulb in a building has to go from home AC power to DC light bulb power via a little inverter in the DC light bulb fixture. Off-grid solar homes have other inverters to convert DC solar electricity or DC battery electricity into stable AC output, or just converters to go from DC to DC before going through an inverter to go from DC to AC. These energy conversions can create voltage flicker in cheap LED lights, a problem that can occur with grid connection but can become worse in an off-grid setting. The easy solution is to use high quality LEDs, but that can be a difficult solution to retrofit. Now, the future of lighting may well be powered over Ethernet lighting circuits, providing 24-volt DC lightings directly to the light bulbs, powered by an Ethernet switch and backed up with an uninterruptible power supply. The future of buildings may be renewable solar homes with off-grid capability, but that really isn't where I want our focus to be today. There are smart lighting solutions for AC circuits, so customers won't get left behind by installing traditional lighting systems today. And so for today's class, I'd like us to think modestly about our smart home design. Certainly, there are future-proofing issues to consider in new construction, which could be made today. To me, the Achilles heel is window blinds. Powered window blinds need power brought out to them, and I think it's a good bet to plan for window blinds to be powered over Ethernet. Indoor video cameras are another device which might not be installed in the home today but could easily be tomorrow. And so running additional Ethernet runs to windows and potential cameras is a good future-proofing step in new construction. And then, as a rule of thumb, remember that a hardwired smart sensor is better than a battery-powered one because it can always be on and sensing and communicating without requiring the replacement of batteries as a regular chore. So our smart home still has traditional light switches on the wall and Even if they are smart light switches, they are similar to light switches and are installed by a competent electrician. Because the wires on light switches or the tuck behind controllers are rather tedious and can become safety hazards if improperly terminated. Especially when these behind the box controllers are jammed into the back of the junction box behind the safety switch. I've only used the behind the box controllers, and I feel like a full switch replacement would be easier and improve workmanship and cost about the same. Let's leave our lighting discussion behind to talk about wireless communication protocols within the context of safety. First, these alternative wireless platforms are no more safe than Wi-Fi. One wireless signal is not more safe than the other, in the sense that these communications can still be encrypted or unencrypted. So encryption will slow down the signal, and it requires the other devices which relay the signal to also be encrypted. So sometimes the performance loss on encrypted signals leads to poor signal quality and poor device performance, which isn't preferable for systems that should be responsive, such as security alarms or door locks. A Wi-Fi device, such as one provided by a cloud service like Google Nest or Alexa, can result in hacking issues with customer data being stolen. But at the actual site, that strong Wi-Fi connection with good on-site security can perform better than a lower powered signal such as Z-Wave or Zigbee. Other devices might not need a robust Wi-Fi signal to function, and so can be taken off Wi-Fi completely. An unencrypted, low-energy Z-Wave signal may find it hard to infiltrate a Wi-Fi network, whereas a Wi-Fi device is more likely to be powerful enough to do some damage if it had some malware on it. And of course, encryption is no good if the devices are hacked on the cloud side of the service or the customer side of the service, such as through poor password security. A common practice for smart homes is to select a Wi-Fi router which can set up a second virtual Wi-Fi network that is supposed to be independent of the primary network. The problem with cloud services is that they inevitably want to connect to your personal account, which might not be on the Internet of Things network, as well as to the Internet of Things network. So vulnerabilities ultimately can be difficult to isolate, and sometimes the best is to stay off the Wi-Fi system completely. Local encrypted networks that do not involve use of the facility Wi-Fi do exist, and they can be encrypted, and they do not require a direct connection to the building's internet for their wireless communication to work, and that can simplify the rollout of smart products on facilities where there are internet access concerns by the building owner or manager. These wireless protocols or platforms or signals, whether they're Wi-Fi or Zigbee or Z-Wave, they use different communication frequencies, which offer minuscule advantages compared to each other for particular uses. But that's usually trading off signal quality for reduced cost and increased battery life. So a Wi-Fi device would have great signal quality, but use more batteries and perhaps cost a little more than these lower energy Z-Wave or Zigbee devices. That can change with economies of scale, where the Wi-Fi devices are just made in such great quantities that they end up not really having a cost disadvantage. But these Zigbee or Z-Wave networks are really no more secure than if the same devices were Wi-Fi devices communicating locally on an independent Wi-Fi router or a completely isolated virtual server. Except for the fact that a Zigbee device or a Z-Wave device is less likely to be harboring malware due to their reduced capabilities and smaller distribution channels as compared to smart home behemoths using Wi-Fi cloud services like Google or Amazon. So we're going to conclude the security discussion with the understanding that cloud services are all but inevitable. Having internet in the home means that most people are already purchasing cloud services. Amazon Alexa, Ring, and Nest are no different than Netflix and Disney Plus, or even a cell phone or traditional utility provider, and that they will collect sensitive data in exchange for providing valuable offsite services to the home. We can all agree that security and privacy are good things, and there are options available for customers who prioritize those values, which can be Wi-Fi based or not. The smart home platform that I use is capable of Wi-Fi or Ethernet connections. It's a $40 Raspberry Pi. I then add a Z-Wave antenna to the Raspberry Pi computer via a USB outlet. The rest of my devices are Z-Wave based and do not require the internet to run. Any of these devices would have to use my Raspberry Pi to hack my network, and so only one point of internet connection really needs to be sniffed by a security gateway for any malicious activity. An even more secure device hardware might have more limited functionality. For instance, the host computer not having a Wi-Fi antenna at all, needing a hardwired Ethernet connection to connect to the network, a dedicated mini PC with a Linux-friendly computer processor can serve as a nice host for a home automation machine. The smart home automation platform I use for energy load control is Home Assistant, powered by a $40 Raspberry Pi. The Raspberry Pi has both a Wi-Fi and an Ethernet connection. Let's take a break from the discussion and do a demonstration of how to set up this smart home controller. What we're doing here is building a local device using the Raspberry Pi as the computer hardware. The home automation software Home Assistant will then be stored on the computer. The Home Assistant software is open source software which can be freely downloaded and even expanded upon. This means our home energy controller will not be reliant on a cloud service and will continue running on into the future. The version of Home Assistant I recommend using is Hassio. This is because Hassio is easier for non-coders to connect up with perhaps obscure third-party technical applications. So this is not a problem for basic devices such as the Google Mini or the Amazon Alexa, or other mainstream devices like Nest and smart doorbells and smart speakers. But to set up an energy monitor and data logger, some rather obscure databasing and graphing software will become necessary to use. So we want to do that in the simplest way possible without much programming involved. So first, I will start out by visiting Home Assistant's official documentation. There are many how-to guides for Home Assistant out there. Using the official guides will make sure that you get the proper technical support you need. Speaking of technical support, this is where open source software really becomes fun. Because the software allows for programmers to make contribution to the code, there's a large user community enthusiastic to help you get your energy controller set up. There's a chat program called Discord, which is primarily used by computer gamers to talk to each other, but it also has a following within the technical support community. It is similar to group messaging software Slack, but more like a chat room from the 1990s. Home Assistant has an active Discord community that provides support for beginners and programmers alike. So you won't be alone when attempting to install the open source home automation Home Assistant software onto your $40 Raspberry Pi for the very first time by joining this Discord online community. It's especially valuable for lacking computer skill. Personally, I find this to be the best way to learn about computers. If you have children at home, steering them towards a Raspberry Pi with a home automation build could provide a very solid introduction into computer programming. It's a platform that is technical, but also more friendly towards beginners than other kinds of computer electronics manufacturing that I can think of. As a reminder, use the Hassio installation method because of its add-on capability, which makes it more compatible with more devices without as much programming as compared to the other Home Assistant kind of installation called HASS, that's HASS, which is done either in Docker or within a virtual machine environment for the technophiles out there. So install Hassio instead of HASS. A few different download options are presented for the Hassio software. These are for different kinds of computers which can run Home Assistant. I recommend starting with a Raspberry Pi. That keeps things simple. The need for more robust computing options will be discussed a little later in the program, but a Raspberry Pi is sufficient to implement a modest smart home build. The next step will require many of us to take a step out of our comfort zone. Essentially, the operating system and software need to be installed onto the Raspberry Pi hardware. This step is done using the Balena Etcher program. On Macs, it's called Etcher. To write the code onto a specifically Raspberry Pi friendly memory card. It's a standard data card. The software is then burned onto this memory card. So I got lucky. My laptop has a memory card slot that fits the same memory card as the Raspberry Pi. But already I'm faced with a technical challenge. I'm using a Chromebook, which is not a Windows PC or a Mac or even a real Linux computer, but I need to burn this software image onto the memory card. So my memory card fits into my Chromebook, but Chromebook doesn't have the Etcher software that I need to burn the image file. However, Chromebook has their own recovery tool which does the same thing as this Etcher program. This is a program that would help you create a backup boot disk to a computer. So loading an entire operating system onto a hard disk, your computer crashes, put it in, your computer boots right up because it's running off the hard disk. That's what these Etcher programs or recovery programs do. They allow you to write the image files of electronics operating systems onto a boot disk so the device will start up at power up. So that is what we are building. So I select a local image because I'm selecting the image file that I have locally downloaded onto my computer from the first step. You might think, well, why is it called an image file? Imagine a analog record player, and if you zoom in real closely with a magnifying glass. You can see the little bumps in the record that the needle detects, and that's what plays the music. An image file is the same thing. It's a bunch of ones and zeros that the computer processor is spinning up into your software and boot disk. So it is the image file of what the computer needs to see in order to turn on and use all of its parts. So it tells me to put in my SD memory card. It then says that my SD memory card will be erased to create a new recovery image. I select create now, and within a few seconds I'm done. The next step is to preload the customer Wi-Fi information onto the machine. This involves opening up the SD card and adding a file to it. So it turns out my SD card won't open, and I'm already wondering if I've done something wrong. When I click on it, it won't open. What I can say about flashing software onto hardware, which is what we're doing, is that the instructions must be performed exactly, otherwise it'll break and not work. I run into some more snags, and I go to the Discord group for advice, and the advice is often to follow the instructions. So consistency is nice. If getting off from the instructions results in a mistake, you probably need to get back on the right path. But I still couldn't figure out what my problem was until I realized that by downloading the Home Assistant software, whatever zip program it was using and whatever zip program I was using was removing the title from the zip file. And so I put the image extension back into the file before zipping it up and then reburning a new image onto my memory card. And finally I can open up my memory card, and that gets it working. And so if you walk down a couple of steps into your home automation software and it's not working, that's the right time to stop and go back until where things were working, and try to do things exactly per the instructions. So I want to give the machine Wi-Fi access so that it can download any necessary software it needs to when it boots up, without me having to plug it into, say, my own computer to tell it what to do. A client's Wi-Fi password could be pre-programmed into these machines so that the device would work right out of the box when it ships to site. So I have to create a text file containing my Wi-Fi password and put it in a very specific location on the SD card image file in a folder known as the boot folder. This will load the Wi-Fi password onto the software so that when it powers up, it will automatically update itself. Other configurations could be used to allow the use of Ethernet only. My efforts have worked because the Home Assistant software has created a website at the address of the Raspberry Pi on the local network using the Wi-Fi password access we just gave it. So the Raspberry Pi now has access, and we can log into it and go through their Home Assistant registration process. Already it's recognizing the Google Minis and Chromecasts on my network. I also take the time to register my Z-Wave memory stick by telling the software the location of the memory stick. I actually don't know the answer to this. I don't know the answer to my Z-Wave memory stick USB drive location. But there are plenty of websites out there with the answer, so I simply use the information online. Because the Raspberry Pi is such a uniform hardware, there's many others who have encountered these obstacles beyond yourself when going through the basic process of setting this kind of system up. And by simply learning the answer from a quick internet research, I don't have to go through the process of actually logging into the kind of DOS command line interface to find what the answer to these technical questions are the hard way. It would now be an appropriate time to pat yourself on the back for building a smart home controller from scratch. Later we will add our smart devices to the controller to start managing the electric load. But let's do two more steps first, which will assist the controller's data logging and display capability. The point of this exercise was to show a very specific Hassio installation of Home Assistant. What Hassio gains the user from downloading Hassio instead of the other version called Hass is that Hassio has this add-on store which spares the user from learning much of the hard way on how to program different devices into the controller. Hassio recommends installing the Samba add-on as well as the SSH add-on. Without getting too far into details, this is to promote communication when connecting between the Raspberry Pi and another device. We're going to install the InfluxDB database add-on to store data from the energy monitor. So data needs to be stored in a database. We've added some software to this computer card, but we didn't add any database software, so we add that at this point. When I install the Influx database add-on, I can't initially use it. So I look in the config files, the configuration files, and I go ahead and disable the HTTPS option in order to get it to communicate with my computer over the computer network itself. Over not the network, over the device itself. It doesn't need secure communication to take data that's already being communicated to the Raspberry Pi and process it. So I'm not going to set up a security certificate for that. And so I disable the HTTPS option. After restarting the database and giving it a little bit more time, it starts to work on my Raspberry Pi user interface. There isn't any data in it yet, and I have to create a database called Home Assistant and a username called Home Assistant. I used my Home Assistant software password for this Home Assistant user. So for some case where InfluxDB is communicating with the Home Assistant software, I keep the username and password consistent so that there's no conflict. And now InfluxDB is installed. I do have to remember to go back and give this InfluxDB user full administrative privileges, because the next add-on we're going to install, Grafana, requires those administrative privileges in order to have Grafana communicate with InfluxDB. So the next step is to install Grafana. Grafana is a software that focuses on displaying metrics, so it's very useful for displaying energy metrics. I'll also disable the SSL communication in the configuration file and then start reading through the documentation. So the Grafana documentation suggests to create a new admin user, and I'll create the same user as my Home Assistant user and the same password as my Home Assistant password. The next thing I'll do is add a data source and select InfluxDB as the data source. So Grafana and InfluxDB, are cross-compatible. So, I'll enter in the information, but I still get an error. And so I need to go back into InfluxDB and give my InfluxDB Home Assistant user full admin permission in order to make queries into Grafana. So I go back and give it the permission, come back into Grafana, refresh it, retry it, and now the data source is working. So the Smart Home Hub is now ready for the energy controller peripherals, which we're about to get into, to be registered. So we'll come all back to this in a minute. For now, let's get back into the course discussion. Remember, what we've done here is set up a local home automation controller which can communicate with other devices plugged into the controller, including the host site's internet. This internet access is useful so that the local controller can communicate with cloud devices such as Amazon voice services. This Wi-Fi connection or internet connection is also useful on the local network so that the home automation software can be accessed by phone or computer, provided that user has the Home Assistant password and is on the local network. The internet access is also useful if you wanted to access the Home Assistant build remotely, off-site. However, users will still be concerned about their internet privacy, and at the very least, they'd like to keep the smart home internet device access to a minimum in the interest of internet safety. So for the next few devices that will have wireless communication, we're actually going to register them on a different wireless network, one powered by a USB stick that's called a Z stick for the Zwave wireless network, and we'll be plugging it into the Raspberry Pi. Cloud services, as well as other proprietary services, can have extensive functions, but they can also be relatively limited functions. Now consider the differences between a non-programmable thermostat and a programmable thermostat. The non-programmable thermostat can adjust the temperature, but the programmable thermostat can be zoned for each hour of the day and each day of the week. But if I want a programmable thermostat that can be programmed for each hour of the day for every day of the year, I would need something a little bit more capable. And even a $300 smart thermostat like the Rheem EcoNet only has 7-day programming, whereas I want programming for every hour of the day, every day of the year, with even further flexibility to accommodate a variety of on-site energy issues, such as renewable energy or battery storage, and also the ability to save the customer money through advanced automation. So even the $300 Rheem smart thermostat, particularly because they do not have an open API or open communication to a variety of smart hubs and smart platforms, they have a closed network, and so the $300 Rheem thermostat is not good enough for mine. In search of my smart thermostat, what I did was to search for Z-Wave thermostats under the assumption that a Z-Wave thermostat would be a smart thermostat. A myriad of options were available to me on eBay. With any smart device, the version of the software is important. So Z-Wave is now on a Z-Wave Plus version of its technology, and I recommend sticking to Z-Wave Plus components for Z-Wave communication. I would also consider Zigbee as opposed to Z-Wave, as well as Wi-Fi components, so long as they were compatible with my home automation software, and we'll talk more about that later. I chose Z-Wave because traditionally Z-Wave has been cheaper than Wi-Fi devices, but also more intelligent. Well, now many Wi-Fi devices, particularly thermostats, can be found at similar price points and functionality. I would caution that Z-Wave devices can be more difficult to install than their Wi-Fi counterparts, but that does come with some increased functionality, such as the ability to stay off the home's internet completely. At any rate, I went with a $65 Z-Wave Plus thermostat and decided to swap it out with my existing non-programmable Honeywell. Now, remember that National Electric Code defines a qualified person as one who has the skills and knowledge related to construction and operation of electrical equipment and installations, and has received safety training to recognize and avoid hazards involved. So if you are a solar installer and you think you can simply take the thermostat off the wall, you might be surprised to know that it could short out a fuse in the air handler so that the fan will not turn on after you install the new thermostat. This kind of thing is avoided by doing things safely, like powering down the equipment that you are working on before servicing it. But installing the thermostat is fairly straightforward, requiring knowledge of the HVAC system to determine whether or not the home has gas or electric heat, as well as the kind of electric heat provided. The wiring is a little bit tedious. Now, I was working on a larger home where a Google Nest was installed but wasn't working. The air conditioning contractor had not wired the indoor and outdoor unit to accommodate the standard 8-wire thermostat configuration, and so the Nest was not compatible with the Rheem unit. Rheem had their own $300 programmable thermostat that did not need all of those wires to function, but the end result was that the use of that thermostat locked the user into a thermostat that was not programmable from an outside source, and the thermostat only had day of week functions. So that's a shame, because the thermostat on a solar home should be able to adjust with solar production to better manage the intermittent energy produced on site, as well as to manage consumption. But in my case, I want a thermostat to be programmable by time of day for each day of the entire year. Now, here's my thermostat within my home automation software. It has similar functionality to a Nest. A wall-mounted tablet could serve as a dedicated thermostat controller instead of a real thermostat or a hardwired thermostat, while also controlling other functions such as home media players or the lights in the room. To be clear, my Z-Wave thermostat does not provide this level of capability on its own. The Internet of Things has enabled this software to be applied to my $40 thermostat. My utility offers a time of use rate structure, which increases my electricity cost by 400% for 2 to 3 hours per day. It then decreases my rate for the remaining hours by 50%. So if I keep my peak energy use to a minimum, I could save a lot of money. Now, a programmable thermostat could help save money in this manner under a time of use rate without being smart, but a 100% non-programmable thermostat, one that only adjusts the temperature settings, cannot take advantage of time of use metering. So many programmable thermostats can be programmed by hour of the day and day of the week, albeit with some difficulty. But my summer peak times are from 3 to 6 p.m., whereas my winter peak hours are from 6 to 8 a.m., with weekends being off peak. So I'd prefer a thermostat which can be programmed for each hour of the day, each day of the year, in order to avoid having to reprogram it every 6 months. But a simple day of the week, time of day thermostat could work as well without being smart per se. The most important features are the hours of the day and day of the week programming capability. However, the cheapest programmable thermostat I found was $20, and the cheapest smart Z-Wave thermostat was $40, and so I thought that was a reasonable upgrade to pay for additional smart capabilities. Now, the cheapest name brand Wi Fi option thermostat was $90, whereas most of the top shelf options ranged from $150 on up. I went with a $65 Z Wave option. So within my smart home software, I have a home automation menu. I have an automation to turn the thermostat on and off between the hours of 6 a.m. and 8 a.m., which prevents my air conditioner from running during those times. The thermostat is programmed to turn off at 6 a.m., wait for 2 hours, and then turn back on again at 8. I have smart wall plugs which are similarly programmed, allowing me to turn my always on dehumidifier off during peak times and then right back on again when those times are over. So my refrigerator does the same thing. It will run only a small amount during peak times. And my hot water for winter coffee is on a smart plug that is turned on precisely at 5:55 a.m. in order to be hot but avoid peak use. 240 volt smart relays can similarly control 40 amp electric tank water heaters. So controlling energy use in this manner can have substantial savings. By switching to my utility's time of use metering plan and using load shifting to reduce or eliminate my air conditioning loads, refrigerator loads, and using other 120 volt devices to reduce 120 volt loads, I can save 20% on my electric bill through my utility time of use rate structure without any substantial changes to my lifestyle. But Home Assistant is just software. It needs some hardware to host it. The combination of hardware and software to host a smart home is called a hub. Some hubs require internet to function. Other cloud devices may communicate directly with some remote Amazon computer somewhere and not need a hub physically installed in the home. Some hubs that benefit from internet connection can also work locally without internet to control those same devices locally, which means they would still work during an internet failure unless the internet company has some back-end fail-safe to prevent that from happening. Some internet hubs have backup internet connections, like security alarm systems that come with their own data plan built into it for third-party monitoring. So throughout the entire process, the adage of the cloud device being easier, often cheaper, and often more functional, whereas the local device is more costly and more of a technical challenge with some minor improvements of security, largely holds true. So Abode is a security system and it comes with its own smart hub. The hub controls its security devices, but it does not let other devices not directly paired with the security hub to trigger its alarms. So it sets up its own proprietary wireless signal for its own proprietary communication devices. It also has a Z-Wave antenna to connect with some, but not all, Z-Wave devices. It can connect to your home phone and home computer over the home Wi-Fi network or through hardwired Ethernet. That allows alerts to be sent out to the cell phone or to third-party monitors. It has that backup data card for third-party monitoring, and it can also work locally without a monitoring subscription at all. What's interesting about the Abode Hub is the security package can be purchased not just by the year or by the month, but by the week. Some hubs are compatible with other hubs. So the Abode hub can plug into Home Assistant such that the Abode sensors, such as door and window sensors, motion detection, uh, motion alarms, anything involved with a security system within the Abode hub could also be used to drive events in Home Assistant. The Abode hub can plug in to Home Assistant. But when a security hub is plugged into an external hub, that can mean the devices that are paired with the external hub but not with the security hub directly could be prevented from triggering an alarm. So for an alarm system, it is useful to see which components are compatible with the Apple HomeKit or Google Nest or Amazon Ring, Home Assistant, Samsung SmartThings, or other generic hubs. But if you want a third-party monitored service, it is best to start with the security hub and pair any security devices such as proximity sensors directly to the security hub, and then migrate those devices into Home Assistant for additional actions, such as using the door signal, the door sensor, to not only trigger the security alarm but also turn on a light. So what do hubs really do? They manage the specific smart home devices that are directly related to the hub's purpose. Or they're a general hub that tries to manage all the devices in the home. So I can host Home Assistant on a Raspberry Pi. It's a very lightweight home automation software. The Raspberry Pi has a Wi-Fi antenna built right into it, as well as a hardwired Ethernet connection, an HDMI outlet for a monitor, and a couple other useful ports, including USB. The Raspberry Pi as a hub does not come with a Z-Wave antenna, but this can be purchased externally and then plugged into the Raspberry Pi through the USB drive. So is a Raspberry Pi with its limited computing capabilities a good enough hub? I would say that it is good enough for instantaneous monitoring. But there are a few other things to consider. First, for energy visualization and data logging, how much data is to be collected and how much hard drive space is associated with that. It could also benefit from having a backup power supply. And so for a little more money, a smart home hub could not be on a $40 Raspberry Pi, but instead be hosted on a $200 mini computer, which could also serve as a media center for the home and be backed up by a traditional uninterrupted power supply. So some smart home peripherals may require more processing power than what the Raspberry Pi offers on its own, and Home Assistant as the software could be installed on a dedicated larger computer instead. What's more important is how the smart home network is designed to ensure that the system is not overly complicated. So I find Z-Wave devices to be finicky, and I think they would benefit from being pre-programmed into a smart hub off-site before being delivered to the end user. At any rate, Z-Wave communication is not video or audio communication, and so it is relatively easy to communicate through a low bandwidth, low energy modem. This modem can be overpowered if you try to shove a lot of Z-Wave data through it, so it's best not to put Z-Wave to the limits. But it can network together a large number of devices wirelessly without connection to home Wi-Fi, meaning that Z-Wave devices can be pre-programmed off-site and then shipped out to the customer functional wirelessly without needing access to the customer Wi-Fi. Any smart home Wi-Fi devices would then be directly added on site. Now, let's talk through the device registration of these Z-Wave devices within the context of a smart wall plug. So these are power outlets which turn on or off based on a program command, such as time of day, or as a function of the electric load, or as a voice command, or as a simple timer. They can bring intelligence to otherwise dumb devices, and sometimes the dumber the better. The best devices are ones that start up when they get power, not ones that have to have a button pressed after they detect power. So a water heater that automatically starts boiling water when it receives power can be controlled with a timer, whereas one that cannot be set until the power is available would have less smart capability as a retrofit on a smart wall plug. So my dehumidifier is nice because it's dumb. When it has power, it turns on. When it loses power, it turns off. When it gets power back up, it starts back up again. So my dehumidifier is on a smart plug, and it's programmed to turn off right when my time of use peak metering rate starts. But I want coffee in the morning, and my winter peak rate is from 6 a.m. to 8 a.m. when I want the hot water for my coffee. So my dumb electric kettle can be left unpowered but in the on position overnight, and this allows me to preheat my hot water at 5:50 a.m. in the morning by having my smart plug turn on at that time. A push button on the side of the plug serves as a manual override. So registering the smart plug to the hub is a common task. The hub is placed into an inclusion mode to accept the device into its network. There is also a secure inclusion mode for encrypted communications, such as for alarm systems or door locks. But the encryption does slow down the communication, and so I don't recommend Z-Wave devices as security devices. The proximity sensors, the door locks, I would recommend keeping to Wi-Fi if possible, or higher frequency RF communication, such as 2.4 gigahertz, despite the added hacking vulnerabilities that come with Wi-Fi. That is because I like flooding my Z-Wave network with energy data, and the slower encrypted security communication can get flooded out by the large amount of energy use data that I'm trying to pass through my Z-Wave network. That said, I've installed a Z-Wave door lock, and the main concern is that to complete the secure pairing, the door lock needs to be in close proximity to the server. And I had built up a large supercomputer server for my Home Assistant install, which was located in the basement. And so I had to lug my server all the way up the stairs, which involved a lot of wiring and rewiring to get it to a close enough proximity to the door lock for it to pair. But then the door locks work just fine, and the smart capability of a Home Assistant powered door lock gave me an infinitely large number of possible door lock codes, keys, and scenarios to issue different users different keys. But that could have been done with a Wi-Fi door lock as well for a lot less hassle. In any event, the Z-Wave network has a maximum bandwidth it can use, and my energy monitors take up a healthy portion of that bandwidth. And so I would use other hubs or other frequent or other, like Wi-Fi to manage and monitor other devices and leave Z-Wave for energy monitoring and energy controls. This also means I don't have to host Home Assistant on a super fast computer. A Raspberry Pi is sufficient for home automation software needs unless you have a need for other computer related activities such as storing media files on a computer or storing security camera images on a computer, at which point you could build a more powerful computer to manage those functions and install Home Assistant on that as a more central build.
Energy monitors are a very interesting space, which has as much value at the commercial level as it does residentially, if not more. One of the greatest frustrations is how to get energy monitoring data from the monitor into the smart home system. Another frustration is discover that the monitor only transmits and records data for a short period of time. So a longer record, such as a record of the entire month's electrical data, needs to be programmed in accordingly. And so the hub needs additional software to display and record the energy data to make it a bit more usable for the customer. Lucky for us, there are open source data softwares that can expand the usability of our Raspberry Pi hub or other Linux-based computer. I recommend using Grafana and InfluxDB. The energy monitor itself is plugged inside the electric service panel of the home or adjacent to the panel if there's not enough room. They can be powered by the service panel breaker or by a wall plug. As mentioned earlier, getting data from these devices can be a bit of a challenge. There are proprietary devices such as Sense, which use Wi-Fi but are pricey. There are other energy monitoring products more tailored for commercial facilities or multiple branch circuit monitoring that are also pricey and might require a hardwired Ethernet connection, which is not always readily available at the electric service panel. I like using Z-Wave for energy monitoring because I can purchase a generic Z-Wave service panel monitor that isn't connected to any proprietary platform like Sense. In fact, this can be its own problem because it comes with absolutely no software, and so it will not work by itself right out of the box. It will only work when connected to a smart home hub. But this energy sensor is $90 instead of $300, and it allows for wireless communication back to the hub. And since it's Z-Wave, it doesn't require wireless communication to the facility internet to get its signal back to my smart hub. And so my entire energy manager will only be connected to the internet system at the hub itself, rather than have all these diverse wireless devices peeking into the customer's internet. And so my energy controller, by being a Z-Wave network, has fewer internet security concerns to the site host, which is perfectly fine so long as the Z-Wave network is not so complicated as to exceed its own capabilities. So as far as national electric code goes on electric service panels, it's evolving, but the basics are important. These consumption monitors can only fit inside the service panel if they do not fill more than 75% of the cross-sectional area of the service panel, which is typically a depth constraint from the back of the box to the front of the box. I think it's best to plan a power circuit and conduit pathway somewhere near the side, near the top of the electric service panel to host these service panel monitors if possible. Here is a picture of the popular consumption meter Sense. Home Assistant is compatible with Sense, so time of use metering rate could be optimized with Sense, and there's no problem with that other than the payback will be longer because Sense costs $300. Here is a picture of the popular consumption meter Sense. Home Assistant is compatible with Sense, so time of use metering rate could be optimized with Sense, and there's no problem with that other than the payback will be longer because Sense costs $300, whereas the actual hardware required for the same data could be had for one-third that amount. But at the end of the day, you're ending up paying for Sense's code or having to figure out how to do the code yourself.
First, the consumption monitor is installed inside the electric service panel. Because I rent, I'm running the power monitor to an external power outlet out the bottom of the service panel. But it could easily be powered within an available breaker space. The user manual is consulted to confirm the orientation of the current sensing transducer clamps, and it is noted that the power supply must be on the first leg of the power of the first clamp. If the power outlet is powered by leg 2, I would reverse the clamp orientations. The Smart Hub is then placed into inclusion mode. I'm not using this hub for security devices, and so I will not be using the pair secure option. After inclusion, the device shows up as a node in the system. When the device pairs, the first thing to do is relabel all of the entities which are created along with the node, which relate to the device just paired into the system. A simple on-off switch, like a Windows sensor, might not have too many entities that get registered automatically within Home Assistant. An energy meter, which measures and reports a wide range of data such as current and voltage and temperature and energy, power. It can have a wide range of data with quite a few entities to relabel. However, failing to relabel these entities will result in a messy database down the road. So the best thing you can do is relabel all the entities every time you register a new device into Home Assistant. These entities themselves can be accessed and relabeled in a couple of different ways within Home Assistant. In this case, 3 entities are created. The energy monitor has 2 clamps. So it's likely that the 3 energy meter entities represent clamp 1, clamp 2, and then the combination of data from clamp 1 and clamp 2. Relabeling these entities properly will eliminate the guesswork when using these entity names elsewhere, such as in our code automations. So while it may seem tedious, relabeling these entities is a critical task that you do at device registration. A nice thing about Z-Wave networks is this work can be completed off-site remotely before the items are sent to site without knowing the client Wi-Fi information. And so most of these devices already communicate and are pre-programmed with the hardware being staged off-site. Now, I don't know which of the 3 meter entities represent the power consumption of the entire house. And so I'll use some visualization cards in the Home Assistant user interface to show more information about the home power consumption. In addition to a direct numeric reading of the sensor, Home Assistant has a gauge view built in, which can change the color visually as the power consumption rises and falls. While this is not the only way to visualize the data, I can use these gauges to easily see that energy meter entity 1 is the whole house consumption, representing the combined data of energy meter entity 2 and energy meter entity 3, which would represent leg 1 and leg 2 of power for the home. By clicking on the entity, roughly an hour's worth of real-time consumption data is revealed, but I'm not able to zoom in on or preview the days or previous days records. Additional software is needed for that level of data management. This is more of a real-time sensor readout, and that might be all you need. Right now, the real-time value of this data can be used in our available home automations. And so this may be enough data to get started. For example, to put the dehumidifier on a load leveling mode of operation, it is a simple matter of telling the smart plug to turn off whenever the whole house energy consumption meter exceeds 4,000 watts. The same could be done for any 120 volt wall plug device. Every plug-in refrigerator, dehumidifier, water heater, and more could be fine-tuned to stay within the parameters of the off-grid solar system or the demand-based electric rate structure.
Almost immediately, the home consumption data is available and plugged into the automation network. Knowing the home consumption is useful for demand management, such as for kilowatt demand charge management or off-grid living. I have a client who's powering a 5,000 square foot all-electric home on a 12 kilowatt battery inverter. And the only way she gets there and staying within the parameters of her off-grid inverter is to have certain electrical loads turning on and off as a function of her building consumption. So her hot water tank only charges during off-peak times, and her refrigerator only chills the food during off-peak or mid-peak times. And so when her air conditioning turns on and bumps her electrical consumption up to the peak limits of the inverters, it turns other loads off so that the inverter can manage the load and not turn off itself, which would result in a loss of power to the entire house. Getting the numbers to display in a nice and consumer-friendly manner logged into a database requires a little bit more work than simply evaluating the numbers in real time as they are being passed through the consumption meter. With open source projects, you can do a lot of hacking, and the end result can be something that is either cheaper or nicer, or perhaps both, than what products already exist. Many share in this spirit and publish the code and work processes they've encountered, which can help you assist your own efforts, so that InfluxDB and Grafana, which are rather technical computer softwares, one's for database management and the other is for displaying data in database management. These are free and open source softwares with plenty of online instructions to walk you through how to set them up with a Raspberry Pi. So if done correctly, then that data that is being tabulated and calculated by Home Assistant should then be able to be stored into the InfluxDB database, where it then can be displayed by Grafana and even plugged back into Home Assistant for a better visual display. Now, the idea of doing this technical programming may not appeal to you, and the price of the Sense consumption meter may not appeal to you either. Consumption meters are helpful in visualizing energy use, but they're not actually necessary to save money under time of use metering. The Home Assistant software will already know what time of day it is, and if the parameters are simple enough to avoid energy use during a defined period of time, you don't really need a consumption monitor to tell you anything other than real-time data usage. And so maybe a simple monitor that only tells you real-time data energy usage be all you need for checking in on your energy controls. And that is not too complicated, unlike setting up a database and logging data to that database and getting it going. Although that too was a lot easier than I expected, having some computer skill but never done stuff like this before.
Let's get back into our home energy controller build. There's a few things we need to add to improve the overall system elegance. First, let's add the room where the service panel monitor is installed as an area within Home Assistant. It's best to create these areas as needed. It's sometimes nice to restart the Home Assistant server from within Home Assistant. Our simplified installation glazed over a few programming steps. In the alternate version of the install, the computer would require a command line interface command that you type into the computer in order to start the system up. In this case, I want to populate Grafana with energy data and create an InfluxDB database. And those may need a system restart after installation in order for the data to populate. When I pull up InfluxDB, it still isn't working, and I suspect it's because I skipped an instruction which told me to edit the configuration YAML file for Home Assistant. This is another file which is hidden outside of the Home Assistant user interface. However, I installed a configurator add-on within Hassio, which allows me to edit the configuration.yaml file from within Home Assistant. Otherwise, I would have to use a command line. It gets a little bit more technical. So I added in the InfluxDB code snippet into the configuration.yaml file using the configurator add-on, and then I restart the Home Assistant server. So now that I've given Home Assistant the ability to recognize InfluxDB by editing the configuration.yaml file, when I go to make a Grafana query, my Home Assistant entities are available. So what can I do with this information? The obvious choice is to create an energy graph for my house. Let's start by graphing the energy meter. I do this by creating a dashboard within Grafana. I need to select the data source for the graph. Home Assistant is a database option because of our previous efforts. So the query is a formula that then gets displayed on the graph. So starting out, change nothing about the query that's presented. Instead, just add to it. So we need to add a variable to the query formula. And so I add a power entity for the whole household, which is that primary energy meter we registered in Home Assistant from earlier. Although the data still looks incomplete. Sometimes with these devices, things appear to be plug and play, but they still need some slight programming modification to fit a specific communication need. For example, a Z-Wave network can support over 250 Z-Wave devices at once, but a single energy monitor reporting its data every 10 seconds can take up 20% of the Z-Wave bandwidth capacity, at which point the network does not function well if it's exceeded. But for our needs, we need that granular 10-second energy data because we use it for our energy monitor and we use it for our load controls. And so, we need that granular data. But something still doesn't look right about the graph. And I go into the Z-Wave configuration panel to inspect the energy monitor device specific configuration settings. This is a Z-Wave device, so it will be in the Z-Wave node configuration settings menu. So I could get further into the technical detail of what every individual byte of data represents. But to solve this problem instead, I perform a Google search on what to enter into these settings because inevitably there's someone else out there installing the exact same energy meter onto the exact same Raspberry Pi within Home Assistant who's probably solved the problem already, and often you can find your solutions just through the message forms. And the solution turned out to basically find the reporting settings within the device configurations and set them to, a 5 or 10-second reporting period. Some of these devices were reporting by every 2 minutes instead of every 5 to 10 seconds, and that was causing our graph to look weird. So I then set the settings to 5 seconds, and then on Grafana, I graph to a 10-second interval, and all of a sudden the graph shows a much higher degree of resolution. So I could spend a good bit of time customizing this graph as well as inputting all of the smart home devices on the platform which are energy sensing. For example, the wall plug used to control the dehumidifier will often have an energy sensing option associated with it, and maybe that costs a few dollars more than the smart plug without such feature, but it'll tell us how much energy is specifically being used by the dehumidifier, which is nice because all the service panel monitor tells us is the energy use for the entire building. So our graph can include all of those factors, and it can also be uploaded to the internet, which I use to embed on my website, community.solar, but also to embed on my Home Assistant build main front page, so I don't have to go into Grafana within Home Assistant to see what's going on. So let's clean up our Home Assistant main view in the overview section by taking control of the overview page. Now, I don't want my media players to be the first thing I see. I want a display that reflects my home energy controller. So I create a new tab for the media players to move on to. This is called a new view by Home Assistant. And then I select the right option to move all of these card entities on this overview page. I select the right option to move them onto the new view, that media player tab I just created. I'll also take the web link of my energy monitoring graph and embed it into the overview as an iframe, which is essentially taking an offsite website and displaying it within the Home Assistant platform. To clean up and remove some of these entities that had been auto-created, I use the code editor, which gives me a behind-the-scenes look at some of the code. And sometimes this can be easier or quicker to use than the visual interface. So my energy controller interface is now complete with some automations programmed in. Let's review the economics of implementing a digital load controller onto a home or business. Today, we assembled an entry-level load controller for a total budget of around $350. So let's assume a total professional installation budget by a licensed contractor of $850, with the understanding that if you put the time in and do it yourself, obviously the project could be done more cheaply. Let's also assume that an entry-level commercial project might cost a little bit more than an entry-level residential project, maybe perhaps twice the size, and could be substantially scaled up from there. At the residential level, the best step for energy savings is to identify access to a time of use rate structure. So time of use rates will lower your electric rate for most of the week, but it will significantly increase your electric rate for a few peak hours of the day. My electric cooperative has a good time of day rate structure and even has a 6-month guarantee that any costs that might increase as a result of this rate structure would be refunded at the end of 6 months. But in the summer, between 3 p.m. and 6 p.m., Monday through Friday, I have a peak rate and then an off-peak rate for all other times. In the wintertime, the peak is only for a 2-hour period in the morning, again on weekdays only. So without time of day metering, I get a flat rate of 9 cents per kilowatt hour, and with time of day during peak periods, the electric rate quadruples to 36 cents per kilowatt hour. But during off-peak periods, the electric rate is cut down by half to 4.5 cents per kilowatt hour. So for 3 hours a day, 5 days a week, that's 9% of the year. It's called peak for a reason, so let's fudge the numbers a bit and assume that 10% of my energy use comes during this peak time. I'd call that a worst case scenario event when using a load controller. For example, time of rates could be a longer time frame than 2 or 3 hours. It could be an 8-hour rate. Or certain high energy activities such as intense electric cooking that must be done at 6 a.m. every single day and cannot be avoided otherwise. That could be very punitive for a shorter, more expensive peak time if it can't be avoided at any cost. But that's not the case for me. And if my peak load is a little higher than my average off-peak load, then by increasing my peak rate by 400% and then reducing the off-peak rate by 50% for the remaining 90% of the usage, that starting off out of the gate would decrease my electric rate by 5%. That's if my peak load is not that much greater than my off-peak load. And so right off the bat, using a electric load leveler, I think expecting a decrease in the electric bill under time of use rate structures is easily achievable. I'm more interested in what the savings would be if I substantially upticked my energy controllers, such as turning the thermostat off completely, turning off refrigeration entirely, and then testing to see how long the existing thermal mass in the home can coast through the time of day period while using the least amount of electricity possible. Filling a freezer or refrigerator up with thermal mass, such as bottles of water, could assist this effort, and there's even commercial products for filling your refrigerator with thermal mass, if you're so inclined. But by implementing the measures discussed in class, such as thermostat controls and shifting the dehumidifier, the electric savings for me could be 30% out of a maximum of 50%. The cost savings of 50% being if I used no peak energy and lowered my electric bill by 50% all other times. So that's the absolute top I could reduce my bill. And so I think I could do a healthy portion of that, 30%. So calculating the savings of time of use after the fact is a simple process. The electric bill still contains the total amount of electricity consumed. So it's easy to multiply by that amount by the old flat rate to determine what the electric bill would have been and then compare against the current bill. It's a bit harder to predict load shifting savings in advance, but there is a software which can help. Energy Toolbase is a commercial software which is essentially a glorified spreadsheet intended to calculate electric bill savings with the intended audience of solar or batteries. it's not anything that you can't model on your own, but it is a quick and professional way to graph out the energy use of a system and evaluate different rate structures for cost savings. For example, this building is revealed to have very spiky peak loads. If this were a commercial building being built not based on time of day, but on peak demand, those spiky peaks are a perfect time for an automated load leveling system to take non-critical loads offline. Imagine a hotel where for 15 minutes out of the day, the mini refrigerators would turn off. It would not impact the user experience of the room, but it could create substantial cost savings for the hotel owner. Even lithium ion batteries, which are expensive, can be cost effective in this sort of commercial load leveling. So all the more cheap digital controls are all the more cost effective, and they can work great in tandem. Now, I model my time of use rate with an energy tool base because it doesn't have my rural electric cooperatives time of use rate in their database, which is unusual. They're the market leader in electric rate modeling and structuring. A similar spreadsheet could be programmed in Excel or Google Sheets, but here the interface to get the spreadsheet set up is nice and easy. Now, I have interval data stored in my automation logger. So if I go a year, I can take that data out of my data logger, throw it into Energy Toolbase, and do even more exact bill analysis for even greater insight into time of use savings or battery sizing or solar storage. So data logging serves a real purpose for site planning and should be done well ahead of a project if the building is pre-existing. If I don't have access to this data, then essentially I need to guess how much my energy is peak versus off peak. So I can select, so that's what I do. I just take an assumption that, with my level system, keeping my peak use to be slightly above off peak is a 10% ratio instead of a 9% ratio. So now I can select between the flat rate and time of use rate to more accurately project my cost savings. So I'm modeling 3 different cases. The first is my current electric bill under my current flat electric rate. The second is the cost savings if I get into time of use peak and can manage my peak to have it be about equal to my off-peak use. And then lastly is how much I could save if I take my peak use and reduce it by another 50% and throw that into my off-peak section. So if my peak use is lower and significantly lower than my use in the off-peak time, how much could I save under that scenario, which I would say is the maximum realistic savings without solar or battery to completely eliminate your use during that time. So I found that by doing basic thermostat controls and energy automations, I could expect to save about $300 a year. And if I implemented even more aggressive digital controls, I could increase that to $500 a year saved through time of use metering. Both models assume some peak energy use, which could only be fully eliminated again with a battery. So that's kind of interesting. There are many people who want solar power but can't afford the tens of thousands of dollars in investment as well as the long-term payback. A smaller investment in smart home energy controls can result in a 1 to 2 year payback while adding home automation value beyond the electricity controls themselves into other smart home functionality such as multimedia. Cost savings of $25 to $40 a month on a $160 electric bill by doing nothing but shaping the home electricity use through automation is pretty impressive, I think. The payback on a $350 do-it-yourself project can be under a year. On a professionally installed project, that might be 2 to 3 year payback. On a commercial electric bill, the savings become even greater. A small commercial facility might be incurring a $10 per kilowatt demand charge on all power above 50 kW.
Imagine a hotel owner has a series of 10 240-volt wall air conditioning units. Let's imagine that these are 5 kilowatt units each, most of which are running at full capacity during times of peak demand. Imagine if then we could reduce that peak demand by 4 air conditioning units simply by installing 10 controllers and then timing the units to power cycle in an organized manner. The demand savings from taking 4 units off of the peak load at 5 kilowatts each is a 20 kilowatt reduction in building demand. At $10 per kilowatt, the demand savings would be $20 per month. And so if each relay switch were installed for $200 each, the project could have a 10-month payback. And the material cost of these switches is, $90 when you buy one of them. And so this kind of price point is achievable within digital load controls. If the hotel owner wanted to be more aggressive in his savings, he could turn off all the air conditioners during peak times, resulting in a little more discomfort for the hotel guests, but perhaps an even greater windfall in cost savings. Another 50% increase in the cost savings would push the payback, almost down to 6 months. So in other words, digital load controls are the cheapest way to reduce a facility's electric bill, regardless of whether or not it's a residential customer with access to time of use metering or a commercial customer on a kilowatt demand charge. Now, originally, I thought a smart home should be full to the brim with data collectors. Now, however, smart homes aren't perfect, and it is possible to get carried away, particularly in new construction, filling up the home with smart devices and then failing to be able to bring them all in together in an elegant fashion. A smart home doesn't do anyone any good if it's not functional. So I found many devices are capable of sensing multiple inputs, such as this sensor, which can do motion, temperature, humidity, the amount of light in the room, vibration, and I don't know if I said, I guess I said temperature too. They sense a lot of things. It's called a multi-purpose sensor. But most often you need a sensor for one specific purpose. Is there motion in this area of the house or not? So the other sensing portions of the devices, such as the amount of light in the room, are nice to have in terms of function, but on the other hand, they represent an unnecessary drain on the battery life of the product. So particularly, I would not get too carried away with battery-powered devices in a smart home. Smart smoke alarms are interesting because they can tell you exactly where the alert originated in the house. So if a fire starts in the kitchen, the alert tells you that that is where the fire started. And that can, result in better response times for the building inhabitants as well as for the fire or police department. I was surprised when my dual fire alarm / carbon monoxide smart sensor alerted me that my kitchen oven under its cleaning cycle was giving off some air quality alerts. This information is fun and it can be useful. We cleared out of the kitchen for that time frame, but it does come with a cost. As annoying as it is to change smoke alarm batteries, it is even more annoying to change those batteries more frequently and have to deal with bugs in the system, which might involve pairing and unpairing the smart devices to the smart hubs. Getting up into the ceiling of vaulted ceilings to pair and unpair smoke alarms from the smart device is an annoying task. Furthermore, when a smoke alarm is directly paired to a security hub that has third-party monitoring services connected, it is possible for that alarm service to function as intended, and whenever an alarm is activated, it automatically call the fire department. And sometimes these smart hubs are not capable of differentiating between a carbon monoxide alarm and a smoke alarm, and so you can accidentally call the fire department because you're cleaning your kitchen oven because you have that third party service. So another solution would be to not pair the fire alarms to the security service, but have a audio listener to listen in on when the fire alarms are activated and use an active fire alarm signal to call emergency response teams. So pairing the smoke detectors to a security hub can result in more false alarms being phoned in to the emergency responders, but failing to pair the smoke alarms into the security hub means that they will only function as local alerts rather than have a more automated security function. Regardless, I recommend hardwiring these smart smoke detectors rather than leave them to battery power. Actual wall switches I was less impressed with. My recommendation would be to use full wall switch substitutes that replace the non-smart receptacle rather than adding on behind the switch controllers. Likewise, the touch controllers that I found were either quite expensive or somewhat finicky. The wall remote, for example, is like a magic wand for the home. It's capable of being programmed to do anything. If you have a smart TV that can be turned on and powered by the smart hub and turned to a station, you can program this wall remote to adjust all the lights, the curtains in your room, and really get the mood set for watching your favorite television station. But it doesn't serve as a good light switch on the wall. This is because it is a battery-powered device, and the battery-powered smart home devices need to be woken up before being used. So it doesn't really function as a good light switch because you can't just walk into the room and turn the lights on. You have to walk into the room, take the wall remote off of the wall, press the wake button on the back of it, put it back on the wall, and then you can use it as a light switch. It would be better at initiating a mode such as locking up the house for the night. It serves as a substitute to control the lights in the room while sitting on a chair without the use of your cell phone. So, again, I don't know how useful that is as opposed to just getting everything set up on voice commands. A few months ago, a company called Span.io made a splash advertising itself as a smart electric service panel, and it's staffed up by a bunch of Tesla alums. They are not the only ones in this space. Lumen, Levitron, and even more mainstream brands like Schneider and GE have advertised their own kinds of smart electric service panels. electric service panels are tricky because they're not really designed to be fed from multiple locations, such as a solar array or a generator and the grid concurrently. Home loads are tricky because they can be spiky as well. And so the electric grid helps average out all of our spiky loads together as a society. Our power curve is steady and smooth. When we get down to an individual user, the individual devices clicking on and off can be quite spiky, as can solar production. The problem with backup solar batteries is that without managing your facility electric load, the output power that is required to power an entire home is actually quite large. One heating element inside an otherwise energy efficient air conditioner alone can represent a 10 kilowatt electric load. Now, a residential electric service panel is rated for 50 kilowatts, and so homes can see electric loads for very brief periods of time of 30 kilowatts or more. Just the control electronics necessary for a battery inverter to output 50 kilowatts of power can be $20,000 or more. In other words, the Tesla Powerwall at its $14,000 suggested installation price is going to be too small of a battery and too small of a battery inverter to power an entire house during an emergency. And we saw that this can be okay from an economics perspective to take advantage of time of use metering or demand management. But if the electric grid goes out and the building has a solar array or a Tesla Powerwall on it, and the building loses power because of a grid outage, the inhabitant is going to be aggravated unless they can use their solar array or battery to provide power during that blackout. So the industry is currently solving this problem by wiring up smaller critical load panels, which remain powered on their own output circuit from the battery inverter during grid outages. And this physically limits what the battery inverter can power, which often does not include air conditioning. But the best solution would be to install an automatic transfer switch between the home and the grid, and then manage the home's electrical load to operate within the parameters of the battery inverter, such that the entire home can remain powered up during that outage, just at a lower energy mode.
So some of these companies control and monitor every load on the electric service panel, and some just do a portion. And the end result is an expensive system that might also add value to other more expensive things already on site. But by building a site energy controller, either with expensive top shelf commercial product or more modest open source hardware, the same result is that the system can save the building money on their electric bill while being grid tied, and then also allow for more flexibility of on-site backup power for the whole building during an emergency, while that building is being powered with an undersized generator, such as a gas generator or a solar battery. And that undersizing can result in substantial savings, because otherwise you'd have to build a power system capable of delivering the entire building's worth of power and only using it during an emergency. Not that it's impossible to do so, but it's costly. And so even these expensive top shelf service panel monitors can play a role in reducing a site that's being prepared for off-grid operation. There is one Z-Wave accessory that might initially appear optional, but I strongly recommend getting it if you're implementing a Z-Wave network, and that's a range extender. Z-Wave does not have the range that it advertises, especially when you're transmitting data rich signals. A non critical sensor like a door or window sensor located outside in the yard on a mailbox to notify the home assistant when the mail has arrived, that might be able to transmit a Z-Wave signal over its full range while taking its time to make it from point A to point B over a long distance. Energy signals, which are updating every few seconds with a lot of information, put out more noise onto the Z-Wave network than a simple on-off sensor. And so, although Z-Wave devices are intended as repeater stations, only the hardwired Z-Wave devices actually serve as repeater stations. And so all the battery-powered devices on Z-Wave network do not serve as repeater stations. They only do that when plugged in directly to the wall. So a dedicated Z-Wave repeater station reduces the stress of worrying about the quality of the Z-Wave network. And sometimes it becomes absolutely necessary if your controller and energy monitor are located on opposite sides of the house. So I strongly recommend using the range extender unless the hub is located directly within the utility room where the service panel monitor is located. If you like this program and want your own Raspberry Pi energy controller, why not buy one from me? I will pre-program it for you with a service panel monitor, 3 120 volt smart plugs, a Z-Wave thermostat, a Z-Wave USB stick, a range extender, and all the Raspberry Pi accessories you need to get started at a $499 price point. You won't find a better deal unless you do it yourself. So please allow 2 weeks for delivery.